I see that you are recording.
Um, hmm, no, that's not what I want. Oh, okay, there we go. I think you can let people in.
You ready for me too?
Yeah.
Okay.
Well, greetings, everybody. It's 1 o'clock. I have a strange note on my screen saying my sharing is paused. Uh, are you guys seeing the cover page of the lecture?
We're still seeing the thing to click on it. We don't see the lecture.
I see Microsoft PowerPoint with a bunch of line items.
Okay, well, hang on. That's not what we want. Let's go here and give it a shot.
Now we see it.
Yeah. Is everybody seeing the cover page?
Yeah.
Okay. So welcome. This is lecture 4 of our cosmology class. I am recording this lecture and I'll put it in the class folder so you can access it if you have to leave early or want to see it again. And today we're talking about the dark universe, and I have to define for you what I call the dark universe, because this is not a standard definition. We'll get to that. Let me show you just a recap of what we have seen in the prior lectures. We have this model of the expansion of the universe from the Big Bang to the current state of the universe that we observe, because we can see light from this surface, the cosmic microwave background, forward all the way to today, where we see starlight and galaxy light from nearby objects. So we're seeing all this light that has been emitted by various objects and phenomena in the universe since the beginning of our observable universe. We also have this concordance of overlapping data from multiple different measurement technologies that confines us to a single spot with respect to how much of the universe is matter, that's omega m, and how much of the universe is dark energy. Both of these are dark in the sense that we can't see them directly. So these two topics, dark energy and dark matter, are by definition part of the dark universe we're going to discuss today. And a part of the total matter in the universe, other than dark matter, is the atomic matter that we're made of in stars. And we've discussed several different ways, including this kind of modeling of the concentration or abundance of different species of matter, like helium, deuterium, different isotopes, lithium. And from that analysis of what we observe in the universe, and using the models we have for the evolution of a universe like ours, we find that 4.5% of the universe is in the form of atomic matter. I'll also use the technical term baryonic matter. But again, this concordance tells us that roughly 30% of the universe is matter, and almost all of it is dark matter. We also have observations of galaxies and that data we get, the redshifts that we measure, put us on this green curve, which confirms that our model of the universe is doing the right thing, because this green curve matches the data with these black and gray dots extremely well, but only if you choose these numbers that are captured here in concordance. And here's another way to look at it, the pie chart that we've talked about so much, that dark matter, a fourth of all the energy in the universe, dark energy is 70%. And today I'm going to include neutrinos as an element of the dark universe because, again, we cannot see them. It's not a form of light that we can detect with our eyes or with our telescopes, but it's a form of matter. We now know, and we'll go into detail about this today. Neutrinos are flowing through us at stupendous numbers. And these neutrinos are coming, almost all of them coming from the sun. They all are also produced in nuclear reactions and some scientific experiments, but the bulk are coming to us in enormous quantities due to the processes in the sun that convert hydrogen into helium and lithium and other elements up to iron. And in the process, neutrinos are coming at us at prodigious rates. And here's the breakout of the different types of energy in the universe that make up this pie chart. And this is, again, this is the term we use, baryonic matter. That means atomic matter. And you see here, it's mostly gas in the form of hydrogen and helium floating in between the galaxies and within galaxies, but not in stars. So virtually all the hydrogen and helium in the universe is not in stars. Here's the fraction of the energy in the universe in stars. A substantial amount is in neutrinos, and so forth. So for today's talk, I'm defining dark energy, dark matter, black holes, because again, the object itself is invisible. To characterize or view black holes, as we will today, you have to look at the accretion disk, that is the gas and dust and stars and other things that are in orbit around the black hole that are eventually going to fall into the hole. Black holes, therefore, by my definition, are dark. Neutrinos, so that's what we're going to discuss today. Let's start with dark energy. Einstein did not expect this. Once his equations for gravity were published in roughly 1916, he saw the possibility of putting a parameter into his equations that would produce the prediction of a static universe. That is, a universe that was perennial, that had somehow started an infinite amount of time before and would continue an infinite amount of time in the future. And his equations in 1916 predated the work of Hubble, who actually found expansion in the universe. So everything changed in the course of 10 years, but that ability of Einstein's equations to capture the possibility of a static universe was new. Now, let me check. Okay. All right. I have a couple messages in the chat I'm going to ignore for now. All right. So Einstein did not predict the existence of dark energy, but very soon people began to embrace the possibility that a form of energy in the universe was propelling the expansion that Hubble saw. Now we're going to go through this graph in detail. I know it looks complicated, but it's the way we get our hands on the expansion rate that Hubble found. And what we're looking at here is the different techniques used to build the cosmic ladder we've talked about in the past. That is, if you're looking at nearby objects, you can get the distance by doing geometry that results from Earth's motion around the sun. That's the parallax technique. And that technique also can be extended out into the Milky Way. So you see data points here, these green dots indicate the use of parallax looking at variable stars called Cepheids. These are, I'll remind you, these are the stars that grow brighter and dimmer periodically, and the periodicity is related to their brightness. And we know their brightness because some of them are close enough to us in the Milky Way or the Large Magellanic Cloud that we can measure the brightness because we know the distance to these objects. They are within reach of the parallax or geometric method of finding distance. Again, I'll remind you that finding the velocity of objects in the universe is straightforward. That comes from redshift. So any telescope equipped with a spectrometer can take a picture of the light from a distant galaxy and detect the presence of various elements, oxygen, hydrogen, nitrogen, and so forth, and match that spectrum to what we find in the laboratory here on Earth. And the shift that we find is the redshift I talk about so much. That results from the velocity of that distant galaxy relative to us. So by using geometry and variable stars, we can begin to build a ladder, and this diagonal line is that ladder. And the ladder means that we know the distance to these objects. So here's a Large Magellanic Cloud. Here's a nearby galaxy. This number refers to the work of forgot his name. And so we go out into the universe using geometry and Cepheid variable stars to measure these distances. Then we can transition to finding Cepheid variables that happen to be in the same region as type 1a supernovae, particular type of supernova. And that gives us another expanse that we can cover and as we build our ladder. So the blue dots represent the use of variable stars to measure the distance to exploding stars called type 1a supernovae. The next step is to use the supernovae far beyond the region where we can see Cepheid individual stars or Cepheid variables. And then we have all these red dots, which are supernovae, which have been calibrated using Cepheid variables, and the Cepheid variables have been calibrated using the parallax method. So the ladder goes all the way out to great distances. I'll show you the distance here in a second. And that's what this fat arrow is indicating to you. The farther we go along this diagonal line, the farther out away from Earth we are reaching. So here's what I just said. Cepheids used with parallax and calibrated to the energy output of type 1 supernovae gives us the reach out to this regime here. And the redshifts that have been achieved with the Hubble Space Telescope let us use this ladder to get out to this distance, 17 billion light years, in a universe that, remember, have the look back distance indicates the most distant object, which is the surface of the cosmic microwave background, is about 45 billion light years from us. And these are links that you can use to get more detail. We even have some recent work by James Webb Space Telescope that have gone to even higher redshift beyond what's on this drawing. And let's look at some distances, the specific distances. In the Milky Way, in its vicinity, we can use parallax to look out about 3,000 light years. If we extend that and employ the Cepheids that we see in our neighboring little piece of a galaxy called the Large Magellanic Cloud, we can see out to and measure distance out to 150,000 light years. The next step is a big one. We're out to 2.5 million, then 20 million, 100 million, 200 million. By the time we get to this point, we have calibration of the supernova events out to 200 million light years and beyond. So all the information we have about the distance to the most distant objects is coming from these type 1a supernova events. So there's 1 billion light years, and here we are at roughly 9 billion light years and a redshift of 1.3. Notice, I'll go back over here, notice that we now, using the much bigger, much more sensitive James Webb Telescope, we can get out to a redshift of about 3, which is a dramatic increase that provides a great deal more reach for our ladder. The green bar is the range of supernova events that were used to detect the accelerating expansion of the universe in the late 1990s and led to a Nobel Prize. So the objects here, these distances here, are not far enough to indicate the expansion of an accelerating expansion of the universe, but these supernova events here were able to do that. Now, James Webb is repeating some of this work, and in this panel here, you can see the gray dots come from looking at supernova events using Hubble Space Telescope. The red dots come from James Webb. And if we expand this, you can see the range of deviation from this mean by the James Webb data is much tighter than from Hubble. The James Webb is a bigger collecting area and more sophisticated instruments. And so this information from James Webb is going to refine what we know about this part of the ladder, and then it'll help us out here. And new results are coming all the time. Here's an example of type 1a supernova at redshift 2.9. Now let's take a look in detail at what the Hubble telescope provided once it was repaired in 1993. So let's start with this little set of data here and explain what this is. There's our expected value for the amount of matter in the universe, omega m, and here's the amount anticipated for the amount of dark energy, and there are 4 different possibilities drawn on this map. So this one, that there's no matter in the universe, of course we know that's not the case. That's this dotted line. Then we have a 50-50 split between matter and dark energy. That's this dotted line. Then there's a possibility that the entire universe is made of matter with no dark energy. That's a dotted line that's hidden right here. And then there's this bizarre one here that has a dominant amount of matter and negative dark energy. That is a different characteristic for the dark energy, and that's this dotted line here. And then smooth lines have been drawn through measurements made. In this case, all these yellow dots, these are the redshift and brightness of galaxies or other objects visible from the ground. So this is referring to a particular telescope research done from the ground, and it's rather limited because the telescope has to look through the atmosphere. The supernova research that started around 1995 gives us these red dots. And it's a little hard to see here. I'll show you a better way to look at it, but you can see a trend for this group of supernova events to lead toward this or somewhere in between. And the answer turns out to be somewhere in between these two conjectures. That's where the supernova data made its impact. Here's another way to present exactly the same data. We just expanded this scale and this scale. And now you can see very clearly, here's the Tololo data from the ground. Doesn't really help us separate the various possibilities. But when you look at the supernova data, you can see most of the clustering of the data is between this possibility of no matter and all dark energy and this dotted line, a half 50-50. And the answer, turns out now we know the real truth about our universe is right in between, with 30% matter and 70% dark energy. By the way, in the cases here that add up to be 1, that implies a flat geometry for the universe. So this is the data that led to a Nobel Prize for Perlmutter and Rees. Perlmutter led a group on the West Coast, and Adam Rees led the group in Baltimore using the Hubble data and other data, and show the universe is expanding at an accelerating rate. There's another way to look at it, almost the same, except now we're focused on the solid line with 30% matter and 70% dark energy. And you see the references, the dots are assigned to the two teams that did this work. And the answer lies right on that curve. And James Webb is redoing a lot of this to understand the expansion rate more accurately. So this is the result that we know about. So dark energy seems to be compelling the expansion of the universe, but there's more than one piece of evidence. We do have the supernova data, but we also see in the details of the cosmic microwave background and the baryon acoustic oscillations the same number for the expansion rate of the universe compelled by a dark energy, and some other things as well. So the key thing is the supernova data, but these other sources of data complement what we know about the supernova data. And I'll just remind you about baryon acoustics. This has the property that the galaxies we see today have formed essentially at locations where density in the early universe was highest. And we can see those high density regions by seeing the coldest spots in the cosmic microwave background. And that's what this depicts. So this is really related, this baryon acoustics is actually related to sound waves that would have been available to hear in the early universe had we been there. And people have actually translated the sound waves that are extractable from the cosmic microwave background, converted it to frequencies that humans can hear. And you can hear the moaning and groaning of the early universe as it was going through its birth phase. So this accelerating expansion of the universe depicted here, that this is the expansion rate. I've shown this in different forms before, that the expansion rate was much higher in the past. It was slowed initially because the matter in the universe that was present had gravitational influence and slowed the expansion rate until about 7.5 billion years after the Big Bang. And then by then, the universe was big enough and had enough dark energy that dark energy took over, and we expect we're on this trajectory. And you've seen this before. I just showed it. These are this is data from galaxies influenced by baryon acoustics. And the green curve is the use of the Friedmann equation with the parameters 0.3 and 0.7. And that seems to match the observed data extremely well. So where did this dark energy come from? And we're going to take a little detour and talk about the work of Casimir, a Dutch scientist, in the 1940s. In the late 1940s, progress had been made on an improved way to describe quantum mechanical properties of the subatomic world. And Casimir was a very creative scientist, and he concluded, let me show you his picture, and what he said is a vacuum is filled with quantum mechanical particles allowed by the Heisenberg uncertainty principle. We won't go into a lot of detail about that. If you take my class on quantum mechanics, you can get all the detail you need about the Heisenberg uncertainty principle. But the idea that Casimir came up with is the Heisenberg principle allows for the spontaneous arrival and disappearance of particles and light, so long as it does not violate the Heisenberg rule. That means that if you take a vacuum, a perfect vacuum that he conjured up, it's filled with particles of all kinds of wavelengths and all kinds of behavior. But if we insert into that vacuum two mechanical plates and put them extremely close together, the particles and light that spontaneously appear and disappear in what is called quantum foam, the long wavelength pieces or particles cannot fit between the plates. The short wavelength pieces can fit. So what he imagined is outside of this pair of plates, all wavelengths exist. Inside, only the shortest wavelengths exist. That means the energy level between the plates must be lower than the energy level outside the plates. The analogy I often use is if you go skiing and when you leave the ski slopes and you buy a bottle of Pepsi, drink some of it, and then put the cap on up in the mountains. As you drive down the hill, you may hear some creaking and groaning in the back of your car because the higher pressure in Denver can crush the bottle, which contains a lower pressure. It contains the pressure that you captured or trapped when you put the lid on up in the high mountains. So that same sort of thing is what Casimir was thinking about, that there should be a force between these two plates, forcing them together. And he did a very elaborate calculation and predicted this black curve. For the force between the plates, depending on the distance between the plates, and notice this is in nanometers, these plates have to be extremely close together, and measurements eventually were made. It took 50 years to design the experiment. The little squares represent measurements. The dotted line is just a technical detail. If those of you with a math background, if you want to see the calculation that Casimir did, I can show it to you. Here's the point. Casimir predicted that empty space has energy in it. These spontaneous fluctuations are the so-called quantum foam. And he was criticized, but everybody began to respect what he did when the experiment was finally conducted in the early 1990s. Here's a depiction of quantum foam. It's just stuff churning and boiling all around. And here's the Heisenberg uncertainty principle that says energy can appear spontaneously if its lifetime is short enough so that the product of the amount of fluctuating energy and the lifetime of that energy is greater than this tiny number. So this is a now accepted feature of the quantum world, that the empty space is filled with a churning foam of virtual particles, as long as those particles satisfy this. And for a time, people thought, if Casimir is right, perhaps that churning foam is what is propelling the expansion of the universe. Now, of course, he did his work prior to the measurement of the accelerating expansion of the universe, but these things were being discussed when we finally got the data from the Hubble Space Telescope and did the data analysis and indeed found an accelerating expansion. And so the question was, is Casimir's effect, the vacuum energy, is that the source of an influence in space between the galaxies forcing expansion? And so the astronomers were eager to say, yes, we know what the expansion, what the energy is that's compelling expansion of the universe. Meanwhile, in the laboratory, people by the early 90s had measured the Casimir effect. And I've already shown you the graph showing that Casimir effect agrees with his theory. So we know we have a truth to that part of the problem. And the question is it the same effect that's compelling expansion of the universe? And the answer is no, it's not. The difference between these two things, the energy level required to explain expansion of the universe, is tinier by this factor than the vacuum energy we measure in the laboratory. That is a stupendously large number. And here's a typical statement you'll hear the professionals make about this situation. The prediction that the astronomers wanted to make for the expansion, the energy of expansion, is the worst prediction in the history of physics, because the laboratory measurements indicate that the energy density needed to explain the expanding universe is 10 to the 120th times too big. And we're lucky it is, because if the vacuum energy found in the laboratory was the one compelling the expansion of the universe would have expanded so quickly that no star would have formed. You just end up with a universe with separated hydrogen atoms, never able to cluster into stars and make heavy elements and eventually the star that we orbit. So there's no explanation for this right now. Dark energy and the Casimir energy are woefully different. That's 10 to the 120th. It's a stupendously large number, and everybody who cares about this has a headache. So we just don't know why dark energy is so different from the vacuum energy that Casimir predicted. And what's more, why is it so small? It's a good thing it is, but this remains a mysterious property of our cosmos. So that's a summary of the one topic of darkness that I want to talk about today, and we have others to discuss as well. Dark matter is also dark. We have many compelling reasons to understand its existence. We can measure its properties, but the reason it exists is not understood. So we see here in the 1930s, Fritz Zwicky, a Swiss astronomer, looked at the behavior of clusters of galaxies. That is, if you have a cluster is typically defined as a group of galaxies that are gravitationally bound, and there may be somewhere between hundreds to thousands of galaxies in these clusters. And Zwicky had the technology to look at their relative motion and concluded that there was something invisible influencing the way those galaxies were interacting gravitationally. The topic languished until after World War II. New measurements were made, and Vera Rubin studied the dynamics of individual galaxies and found a similar conclusion, that there's something out there that's invisible, that doesn't interact with light, so we can't see it with our telescopes, but it is dictating the properties of stars moving in the galaxies. Currently, there's other sources of evidence that confirm the idea of dark matter as a gravitational force, but not interacting with light. So as a result, we can't see that whatever it is. And you see a list here I'm putting up of different types of evidence for the presence of dark matter. The modern interpretation is that galaxy formation in the early universe needed dark matter. Otherwise, we would not see the galaxies we see today. We would see vastly different kinds of structures. There's Fritz Zwicky, notoriously grumpy old man. There's Vera Rubin, and she has now this spectacular telescope nearing completion that is designed specifically to look for evidence of dark matter. Here's the easiest way to depict what Vera Rubin saw when she studied individual galaxies. If we look at the center of a galaxy, so this is the galaxy we're thinking about, there's the center, and we look out radially. This is what we get from looking at the density of stars. Now, to this point, we can identify starlight, and I told you last week, using redshift, we can detect the velocity of the stars. We can look at the chemical composition, pick out some prominent example species, like mostly hydrogen, and from the hydrogen, we can look at the hydrogen out in this side of the galaxy and see it receding from us. And we can look at this side and see it approaching us because the galaxy is rotating. And our systems are now sensitive enough to measure the velocity. And that's what we're plotting here. So Vera Rubin concentrated on using redshift to find the velocity of stars in this region and this region, and she could get the velocity, and that's from the starlight. You can also get it from the gas that floats between the stars in the galaxy, and this curve tells us how the galaxy is rotating. But if you then go look at Newton's equations for gravity and try to plot a distribution of matter that would produce this kind of curve, you discover an anomaly. That is Newton's law, based on the stars and gas we can see. Newton's law says we should see velocities that do this. So it would have a maximum right here, and then lower velocities out in the far reaches of the galaxy. These galaxy curves were studied by Rubin and her students for decades. And every galaxy they looked at had some behavior like this. Unexplained behavior. One explanation, not the only explanation, but one explanation is that this galaxy is in a cloud of dark matter that was probably pertinent or important to the galaxy's formation in the first place. And the presence of this cloud of dark matter can explain this curve. I say it's not the only explanation. There's an idea that this behavior by galaxies can be explained by a subtlety in Newton's law of gravity. That's been explored for decades. And smart people have invested a big parts of their careers working on this problem. And they can make the case that Newton's law of gravity doesn't work far from the star, and the result is you get this kind of behavior. The problem is we have other observations about the amount of dark matter that are not explained by altering Newton's law of gravity. The most prominent one is the cosmic microwave background. I'll talk about that in a minute, but almost everyone thinks that there's a cloud around and within each galaxy that participated in the galaxy's formation, and that cloud is just sitting there and has been since the beginning of the galaxy. One of the key ways to challenge the idea that Newton's law of gravity is not the answer to this dilemma is the bending of light by galactic clusters, where we have these arcs. You can see this one, particularly long arc. That streak is coming from a compact galaxy far beyond an intervening galaxy, and the intervening galaxy and its dark matter have altered the path of the light rays and produced this streak. See, this is a very prominent streak here. That's not the shape of the galaxy that produced this light. Galaxies tend to have these kind of compact spiral shapes or clouds, dense clouds. There's another spiral. So the trajectory of light in the universe is another factor in identifying and actually mapping dark energy and adding to the evidence for its existence. So there's a discussion here that this galaxy cluster, this one, Abell 370, has hundreds of galaxies bound together by gravity, and the combination of the gas and dark matter in this region are not observable, but they've altered the path of light propagating from even more distant galaxies. So lensing is a factor. Here's some more profound examples of lensing done by James Webb Space Telescope. All this is part of a single compact galaxy whose light has been altered, traveling past a gravitational influence. And in a large number of cases, that gravitational influence is dark matter. So you see, Hubble took a picture of this spot on the sky, and Webb, 10 years ago, and Webb has improved that importance, that observation. We even see these kinds of things. We see these what are called Einstein rings, where a distant object, the nearby object, and our telescope are all aligned just right, and the light forms a ring. All of that light's coming from a distant point, but the pathway the light takes is altered by the intervening galaxy. So here's some more information about that. Here's a depiction of this process. There's a quasar, a highly energetic galaxy with a supermassive black hole generating a stupendous amount of energy, and those light rays are headed to our telescope over here, but there's an intervening galaxy, and so we get almost like a lens producing multiple examples. You can call them mirages. And each one of these bright spots we see are coming from this. And we can tell that they're coming from this because all four of these have the same redshift, the same chemical composition, and most important, this quasar, the supermassive black hole in the quasar is active. It's digesting whatever it can find to chew on. And when it has plenty of fuel, it brightens up. So if we look at the brightening and dimming of these four spots, and I'll slide them left and right with respect to time, they map right on top of each other, telling us that all this light, these four bright spots, came from that one quasar. And a big part of the influence that occurred to create this lensing effect is coming from dark matter. Here's another Einstein ring. Here's four. This cartoon was probably derived from this particular example of what's called an Einstein cross. Here's yet another way to depict it. Here's that distant light source. Here's our telescopes here at Earth and the intervening galaxy, and a very nice Einstein ring. Now let's stop at this point and see if people have questions about what we've been talking about. Nope.
And there's a couple of questions in the chat section.
Yeah, I've just pulled this up. Yeah, it looks like there's a typo, which I will fix. How do we know that Cepheid periodicity is proportional to luminosity? We get this from the work in the early 20th century from Henrietta Leavitt, who measured luminosity of stars that have this pulsing property, this brightening and dimming. And she did it for many, many stars and discovered that there's a relationship. I showed it last time. There's a relationship between the periodicity and the brightness. And that only worked because most of her work was done on the Cepheid variables that are in the Milky Way, so we can get their distance by looking at parallax. And the Large Magellanic Cloud, which is a neighboring small galaxy that's in orbit around the Milky Way, it also has Cepheid variables. So if you look at last week's lecture, you'll see examples of the periodicity luminosity relationship. Let's see, is there a shape to the... Oh, okay, so Dave is asking about the shape of the cloud. I'm going to show you some examples of measured cloud shapes, and whether, I don't think we get this for each individual galaxy, but we do get it for the universe as a whole. So let's, if those are the only questions, let's go ahead and I'll show you a three-dimensional map of the cloud of dark matter that exists between us and a distant spot in the universe. So here's the cosmic microwave background. We've talked about this many times, and it turns out that the position and height of this peak is indicative of the amount of dark matter in the universe. And it's clear that the green curve is a smooth fit through data points derived from this measurement of the cosmic microwave background using a model of the universe that I showed you last week. And that model really works because you see this, the thin green line there that goes through all the data points. That model and the little undulations you see in the data captured here matches extremely well. The question, and to get it to match, you have 6 parameters that you can tinker with. And if you get all 6 right, you get this agreement If you don't have all 6 right, you don't get agreement between the green line and the data. And this point right here is particularly sensitive to your choice for the amount of dark matter in the universe. And it agrees with the other sources of data I showed you when I showed you the concordance early in this presentation. So dark matter is a factor, and it's detectable by the height and position of that peak. And it rejects the alternate method of explaining the behavior of galactic stars. I mentioned is a proposal that Newtonian gravity has to be altered to explain that. And this idea of modified Newtonian gravity called MOND can't explain this. The debate goes on, but I think it's like 95-5 partition between astronomers about which idea is more correct. Is it dark matter in and around galaxies, or is there something exotic about Newton's law of gravity? Here's another piece of proof. This is called the bullet cluster, and you can see why. It looks like this bullet has passed through this, and in fact, these are collections of galaxies, one area passing through the other. And the blue is the cloud of dark matter involved in this, obtained by looking at the dynamics that is seen here and by using the lensing effect of the dark matter. So you see this separation. And in fact, well, first of all, the bullet cluster is really 2 clusters, and there's 40 galaxies distributed throughout here. And there's a way, I guess it's on the next page, you can actually watch a video of different strategies for trying to reproduce this shape. Yeah, here it is. You can go to, if you just click on these, you'll jump into a YouTube analysis where they take 2 clusters, this one, and let it pass through the other and figure out which one of them produces this effect. And the only way you can get this effect is by having this cloud of dark matter around to influence the motions of the stars in these 2 clusters of galaxies. So you can see here, they put some dark matter there or less there. Here, there's almost no dark matter. But the only one that works to reproduce this bullet cluster is the one with dark matter. And this work excludes the possibility that the dark matter is sensitive to itself. That is, that dark matter particles somehow interact. That doesn't appear the case. The dark matter particles, if they are particles, don't seem to notice each other. Unlike atoms, if you pass 2 atoms past one another, they interact because they have the atoms interact because they have electric charge, the electrons that are around the nucleus, and that causes a scattering effect. The electrons interact and change the path of atoms that are near each other. Dark matter doesn't behave that way. So here are some examples that gets to the question that was asked. What's the distribution of dark matter around clusters? These are interacting clusters with a density of, a few hundred galaxies here and a few hundred galaxies here. And you can see that astronomers have teased out the cloud of dark matter. That's the kind of bluish part of these. And there's lots of work going on in this to map the dark matter distribution in clusters of galaxies. In terms of seeing it in individual galaxies, not something I've explored, but I think this is the best way to see it, is the interacting clusters of galaxies. And you see here, this reference deals with a study of 72 clusters using visible light to look at lensing effects and to measure redshift along with X-rays. And you see these maps of dark matter. So these are the features that we know about pertaining to dark matter. Doesn't interact with itself, whereas it doesn't interact with light. And these are, whatever it is, I'll call them particles, whatever it is, it's not relativistic. That is, these are slow-moving objects relative to the speed of light, because a universe with relativistic dark matter would not have formed the galaxies that we see. I've already pointed out that dark matter takes up about 25% of the energy density in the universe. And we know this stuff is stable because it's still present. We can see it in nearby galaxies from light produced, let's say 100 million years ago, rather than in the early universe. If dark matter was made up of not permanent material, but material like radioactive material that decays, we wouldn't see it in the local structures around us in the universe. And as I mentioned, and I emphasize here, there's no strong mechanism for dark matter to interact with itself or ordinary matter. That means that it doesn't settle into the center of galaxies. Any object that's near a galaxy will, over billions of years, find itself influenced by the gravitational influence of the galaxy and will drift toward the center of the galaxy. But as I've shown you, the measured shape of the clouds of dark matter don't exhibit that. The dark matter is outside and between galaxies. That indicates it doesn't have a mechanism for losing energy, and probably means that dark matter cannot fall into a black hole, because for something to lose energy and fall into any gravitational field, it has to have a mechanism for dissipating energy. And atoms do that by scattering off of each other. And when they do, they radiate photons. They radiate away energy when they interact. Dark matter doesn't seem to do that. And so we don't see it clustered around the center of galaxies. So here's a little box of mystery from NASA asking, would you like to buy this? Looks like a cereal box, and it says no one really knows what it is, and it comes from the manufacturer General Relativity. Here are some Einstein crosses produced by light propagating past galaxies, clusters of galaxies. And again, we have the image, 4 images of a distant object. And that collection of images was created by lensing induced by dark matter. So let's wrap up by talking about what is this stuff? And so we have 5 different candidates. So we have weakly interacting massive particles that interact using the nature's force that induces radioactivity. And there's work done to try to find these so-called WIMPs, weakly interacting massive particles. There's no conclusive evidence for their existence. Axions are imagined to be non-relativistic, slow-moving particles that don't have any electric charge. And there is work underway to try to find axions. So you can click on that for more detail. Another proposal is that the dark matter is neutron stars and other types of stars that are so dim that we can't detect their presence, and they're made of ordinary matter. But there's a lot of evidence that this cannot be the right answer. That just the behavior of the dark matter clouds we see is incompatible with this as the possible source of dark matter. For example, neutron stars out at the perimeter of a galaxy would eventually find their way drifting inward toward the galaxy, and dark matter doesn't do that. There's this speculated Kaluza-Klein particle that's a fifth dimensional object. That is, it is in a fourth dimension of space, and somehow it leaves its like a Cheshire cat, leaves its smile visible in our world, but we don't have any evidence of that. And the Gravitino is a speculative particle that we should see in accelerator experiments like the ones they do in Switzerland. No such particle has been found. Here's an example of what we get for looking at lensing of light, ancient light coming to our telescope. And this is a map of large-scale structure in 3 dimensions of dark matter. So you make what you want of this. We just don't know what this stuff is. Here's yet another interpretation coming from lensing of the light from distant objects. So let's stop at this point and we'll take a break, and then we'll talk about another topic in the dark universe, and that's black holes. So I'll be gone for roughly 5 minutes, and then we'll resume. Okay, folks, I'm back. Let's go to the next topic in our exploration of the dark universe, and that's black holes. And there's hardly any topic in astronomy that captures the public more than this topic. It's interesting that the equations of Einstein were quickly digested by a small group of people who could follow his theory. And right away they noticed strange objects being predicted, one of which was black holes. Einstein himself never endorsed their existence, and it was just after he died in 1955 that evidence began to grow and the community got interested in black holes. I want to show this piece of art as an example of an object we can all marvel at, a really beautiful painting that I've seen in Paris, but only the artist understood what he did to create this. It's really a work of genius. The same thing applies to music. A non-musician would look at this and say, well, it's just a lot of ink. But we can certainly enjoy a performance of this piece of music. And I use that to introduce Einstein's equation. It's actually many equations shown in a compact form, but we can look at this and enjoy its structure without having to understand the mathematics involved. But here are the key elements of his approach to modeling gravity that ultimately predicts the existence of black holes. One part is the curvature of space-time. Einstein abandoned Newton's idea that there is essentially a rigid spatial structure to the universe, and time carries us from one epoch to another. Einstein proved that the space in which we live can be curved, and it depends on the energy and momentum. That curvature depends on the energy and momentum in the space and the possible addition of dark energy. So let's look at some examples of how this works. The famous physicist John Wheeler had this nice quote everybody uses, that space-time, that is the three dimensions of physical space and time together as a entity, not separated by the way Newton described it, that space-time tells matter how to move and matter tells space-time how to curve. These days, you'll see the word matter replaced by the word energy, because it's not just matter that influences space-time, it's light as well. So matter and light together, we would say energy, how to move, and energy tells space-time how to curve. Again, here's Einstein's equation relating curvature and momentum. And so we find in a simple situation out deep in space, away from any gravitational influence, an object will travel in a straight line because there's nothing there to influence its trajectory. But if we embed some large objects like planets or stars, light will travel along a curved path. It will take the path of least resistance. The actual rule for light traveling in this kind of a situation is the light will travel in a way that minimizes the time between this point and this point. So an isolated object will travel in a straight line But the presence of a massive object here, the sun, can alter the path of light coming from the stars or galaxies. Here, the example we're showing here is one in which you might try to detect the actual position of this star. Its light skims past the surface of the sun and arrives here at our telescope. But because of the path it's taking when it arrives at the telescope, we would have assigned this spot to the star. Now, during the day, you can't do this experiment because the light from the sun is much brighter than the light from individual stars or galaxies. But when there's an eclipse, if we put the moon in here to block out the light from the sun, then this effect is detectable. And in fact, experiments were done right after Einstein's theory came out in 1917. People started looking for possible eclipses, solar eclipses, that would allow us to measure this deflection and see if Einstein's theory was correct. The early attempts made the front page of newspapers everywhere. Careful exploration of those results shows they didn't quite prove Einstein's theory, but 50 years later, people had the technology using various other techniques to actually show that Einstein's theory is for the influence of an object like the sun. He predicts this bending exactly right, and many other things as well. So we have confidence that Einstein's theory is right. Billions of dollars have been spent to try to disprove or further explore Einstein's theory. None of them have shown him to be wrong. It's an extraordinary thing because 100 years of experiments have not revealed any defect in his logic or mathematics. We see these kinds of geometric effects in our own experience. The shortest distance between New York and Paris is not a straight line because airplanes are traveling over a curved surface. The straight line would require over 100 miles of additional flight, flying on a great circle route. That is an arc that passes through the center of the Earth. That's the shortest distance for a spherical object. And light behaves this way as well. Light propagating in a curved space-time does not travel in a straight line. Einstein explains this for us. Now, I've already explained that Friedman and Lemaitre in the 1920s used Einstein's theory to predict expansion or possibly contraction of the universe. Carl Schwarzschild also was working with Einstein's equations, and he found the equation that described the gravitational influence around a spherical object. It doesn't have to be a star. It's just a massive object that isn't rotating. And here's some math, but we're going to take a look at it, not in a lot of detail. We're just going to look at this piece right here. This is Schwarzschild's solution for Einstein's equation for a non-rotating spherical object. And it has this weird thing here. Now, why is that weird? Because under certain circumstances, if your position indicated by this parameter r, your distance from the center of this spherical object, if your distance is just right, namely this becomes 1, and we're dividing by 0. And even those of us who have forgotten all the math that they learned in high school or college will agree we can't divide by 0. And this is why I said that from the 1920, people saw this in Schwarzschild's equation, which otherwise seems to make sense, and wondered, what does this mean? And this, it turns out, now called the Schwarzschild radius, this turns out to be the surface around a spherical object outside of which the universe is the one we experience. And inside of this radius, you're captured by the black hole, never to be seen or heard from again. And it's a simple calculation. The Schwarzschild radius is the number 2 times Newton's gravitational constant, the mass of the black hole, and the square of the speed of light. This is the first indication that a strange object could exist. And we now know this is the boundary around a black hole. So one way to look at this is to cheat a little bit and pretend that this is a 3-dimensional depiction of the influence of the sun on space-time. Well, we can't draw 4 dimensions. We can barely draw, and we can't draw 3 dimensions. We can just cheat because we're working with a flat surface. If we put the sun here, you can see it's distortion of the spacing of this mesh we call space-time. And if you make this object more massive, it's compatible with a white dwarf type of exotic star. The distortion of space-time is more profound, a neutron star even more, and the black hole is so influential and distorts space-time so much that it produces an event horizon as depicted in Schwarzschild's equation. Oh, let me make a little change. Whoops. Let me make a little change here because the text got covered up. It should look like that. Sorry. And we'll go back to presenting. So if we took the sun and compelled it to have a radius of 3 kilometers, roughly the size of a small town.
Ed, we can't see your screen.
Oh, did we lose sharing? Hang on one second. Oh, there we go. Is that better?
Yep, now we see it.
Okay, so if we crush the sun down to have a radius of 3 kilometers, it would be a black hole. And we call this, I'll use the terminology because we're going to repeat this, a 1 solar mass black hole. We've never seen a black hole that small. There doesn't seem to be a mechanism in nature for creating black holes that small. But we do know there's plenty of mechanisms for creating big black holes. And I've already mentioned quasars. That is a galaxy that has a supermassive black hole near its center. And that black hole, depending on its age, might have eaten a big fraction of the available material near it. And we know of at least one supermassive black hole with 66 billion solar masses. Typically, black holes in galaxies represent only a very, very tiny fraction of the mass of a galaxy. For example, this giant, if it were in the Milky Way, would only represent about 5% of the mass of the Milky Way. The Milky Way has a black hole in its center that is about 4 million solar masses, which is a microscopic fraction of the mass of the galaxy. But nonetheless, black holes have been highly influential in how galaxies evolve. And we're very fortunate that we can have discovered the light they produced in the early universe because, again, we can use these very bright emissions from the accretion disk, that is the cloud of debris that's going to fall into the black hole, heated to stupendous temperatures, is a light source that we can use to explore the chemistry and other properties of distant galaxies. That's the quasars I was talking about. So here's another depiction of the distortion of space-time near a black hole, where the black hole is so influential that inside the event horizon located at the Schwarzschild radius, you can't get out. So this would be the boundary. If you're fine if you're outside, you may have to do some work to keep from being pulled in, but that amount of energy is available. Once you're inside here, no amount of energy can get you out. So let's look at a more practical experience that's hopefully none of you have had, and that's being in a boat near a whirlpool. Here's the boat, and it has a motor adequate to keep the boat from falling into this whirlpool. If the motor is shut off, the boat will be pulled in. This boundary for the boat, whether it can escape or stay stationary or fall in, this is equivalent to or analogous to the event horizon or at the Schwarzschild radius of a black hole. The black holes are very simple. They have three properties. They have mass, they have electric charge, and they have have rotation. And where the presumption is virtually every black hole is rotating just because of the mechanisms we currently know about for how they are formed. If there are some exotic formation schemes we don't know about, maybe a stationary non-rotating black hole might exist. But it's also important to recognize that this depiction of how a black hole functions assumes we started with a lake, which has a flat surface, and then this whirlpool forms. In reality, a black hole is surrounded by a spherical surface, so you could approach it from any direction, and you have to be careful not to cross the event horizon because you'll never be seen again. Here's some examples of whirlpools. Now, I've already mentioned the accretion disk, and this artist rendition tries to be pretty complete in its representation of what goes on near the black hole. So the black here is the event horizon. The black hole itself is the singularity at the center. That is, everything that goes into the black hole finds its way to the singularity where it no longer exists. An atom dropped into this black hole quickly would lose its atomic structure. Eventually, the protons and neutrons in its nucleus get stripped into their fundamental particles, the quarks, and eventually none of that exists. It's destroyed as it enters the singularity, which is the smallest thing in the world. It's a little spherical spot in which, in that case I already mentioned, 66 billion solar masses are confined. And the question is, well, where is everything going? And the answer is it's going into curvature. If you look at Einstein's equation again, I'm not going to flip back there, but if you look at his equation, the curvature of space-time is where the energy is invested. And so we have a singularity where all the material ends up, including light. We have the event horizon we've already described. There's light around the black hole, swirling around it. That's called the photon sphere. The magnetic fields produced by heated atomic matter here produces magnetic fields that are tremendously powerful, and they throw debris away. Anything in this accretion disk that has not crossed the horizon could end up getting into this jet and getting thrown out into space at relativistic speeds. So there's lots going on in the vicinity of a black hole. And because of what we know about Einstein's theory of relativity, we know that if you throw something like a book or a tree or a car at this black hole, and if we could clean up this accretion disk so we can actually see what happens as that object approaches the event horizon, the intense gravity of this object slows down the time we observe for that distant object. So if you throw a clock at the black hole, and have that clock designed so it sends us a signal, let's say every second, the closer the clock comes to the surface of the black hole, the event horizon, the longer the time between those 1 second intervals that we designed into the clock. Time appears to slow down, not for us, but for the objects that we have thrown at the event horizon. And we never see the object cross the event horizon. The influence of gravity at the surface of this object is so intense that it appears that time stops right on that surface. So if you throw something in, it appears to freeze on the surface of the event horizon of this black hole. Everything goes into the black hole. And I mentioned there's only 3 properties that are required to describe it: mass, rotational velocity, and electric charge. And the presumption is that all black holes have an electric charge. So here's that depiction again of comparing the influence of the sun and other objects, including a black hole, on the shape of space-time, remembering that a black hole is a 3-dimensional object, but there's no way to draw that. Here's planet Earth, 0.7 of an inch in diameter. If we could create a tiny black hole with the mass of Earth, it would only be this big. The formation of black holes appears to be the result of a collapse of a massive star. It's not the only mechanism that has been conjured up. And one of the things we don't know is which came first. The galaxies in which black holes are found that had enough matter and enough massive stars to create black holes, or did the black hole form first and then attract matter that becomes a galaxy? And of course, mixed into this is the question of the role of dark matter, which I've already told you appears not to be able to fall into a black hole. So this is an area of research. It's the formation and evolution of galaxies and the role of black holes in that formation. So here's language you can read about these. An interesting thing that Stephen Hawking worked on is the idea that black holes can evaporate. And he came up with this formula, which tells us that a black hole with the mass of the sun, put here, this would then become the number 1. A black hole with a mass of the sun would last for 10 to the 67th years, which is a very long time. Remember that our universe has existed for about 10 to the 10th years. The interesting thing is that very tiny black holes, if they ever existed, could have evaporated. If you take a black hole like the one I described for Earth and put that mass in here, even though this number is huge, this number is very tiny, And a black hole the size of Earth would evaporate, let's say, in a few thousand years through a quantum mechanical process. Another feature of black holes is that they have what are called tidal forces. So if you go out in space on a rocket and you hold, here's an astronaut holding two apples, and the rocket accelerates, the two apples will fall toward the bottom of the rocket because, and so will the astronaut, because the rocket is accelerating in one direction. But a gravitational object like Earth or a black hole has a different behavior. And the reason is they're spherical. If you are on Earth, the force you feel drawing you toward the ground is toward the center of Earth. Somebody in Australia is also feeling a force toward the center of Earth, and those forces are not in the same direction. In the extreme case of a black hole, if an astronaut is approaching a black hole, one hand is attracted to the center of the black hole, the singularity, and the other hand is also attracted to that point, but because this is a curved object or spherical object, those two forces are not parallel. So the closer you get to the horizon of the black hole, the more force you feel crushing your hands toward one another. In addition, your feet feel a stronger gravitational force than your head does. So you get spaghettified. You get the squeezing effect and the stretching effect as you approach the event horizon. And it's interesting to take a quick look at how long you could survive inside the horizon of the black hole. Let me make something clear. When you cross the horizon of the black hole, there's no guardian there. There's no surface for you to pass through. It's like those of us in Colorado who decide to go to Kansas. You just keep driving and you cross the border. So there's nothing that lets you know you've crossed the horizon. The time you have to survive inside the horizon depends on the mass of the black hole. So let's take the Milky Way black hole, a 4 million mass black hole. The time for you to get to the singularity is about 60 seconds. But your survival time, based on the properties of human tissue, is only about 9 seconds. And during that 9 seconds, you would have quite an experience. You'd see light coming in from the universe outside the horizon. And perhaps if you had a colleague join you to go through the black hole horizon, you would have 9 seconds to have a quick conversation. You could take a photograph if you wanted before you arrived at the singularity. And of course, nothing you do once you've crossed the horizon can be transmitted to the outside to let people know what your experience was. Now let's compare that to a supermassive black hole. I chose one here, 20 billion solar mass black hole. You have a few days before you reach the horizon, the singularity, and you would survive about 13 hours. This comes again from the strength of tissue. Of course, there's other stuff falling into this black hole which would bombard you with high energy radiation and so forth. But in an idealized experiment, you could survive for a while and fill out a diary that no one would ever have a chance to read. Now, we get the mass of black holes by looking at the behavior of stars that are near the center of the galaxy. And virtually every galaxy appears to have a supermassive black hole. Ours is pretty modest at 4 million solar masses. The big ones are, as I've already pointed out, extremely energetic. Let's take a look at, oh, now before this starts, I've got to do some homework here because I want to show you something, but I got to change my sharing. Well, actually, we could do it this way. You see my whole desktop. These are the trajectories of actual objects near the center of the Milky Way. We'll probably, oh, yes, we're good. Andrea Ghez at UCLA won a Nobel Prize for her persistent work to map the motions of stars near the center of the Milky Way. This is not an animation. This is the real trajectory of stars we can track near the center of the Milky Way. And if you look closely, you'll see that all of them seem to be orbiting around a single point. I'll put my cursor there. And you see how they've animated this to include 20 or 30 stars near the center of the Milky Way. These orbits contain enough information to determine the mass of the Milky Way supermassive black hole. Whoops, didn't mean to do that. We look at yet another example. It's a little more detailed because the techniques get better all the time. Again, this is, and you see the date stamp here, started in 1997 and has about almost 25 years of data showing us that star-shaped object is an invisible object at the center of the Milky Way, around which, let's run that again. There's an invisible object, namely a black hole, that is exerting its gravitational influence on the objects near the center of the Milky Way. And to a large degree, you can use Newton's law of motion for these objects and get the right answer for the mass that is causing their trajectories to be curved. You don't need Einstein's theory. So here's a still picture of those objects. And on the same scale, this little thing here is the solar system. So this is an asteroid, Sedna. You can see it because it has this huge oblong or elliptical orbit, and hidden right there is the orbit of Neptune. So we're looking very, very close to the center of the Milky Way. Now, I mentioned that there are three things that characterize black holes: the mass, the rotation, and the charge. It took from Einstein's theory in 1917 until 1963 to discover the equation that describes rotating black holes. And we have that and can use it to study, make more accurate studies of black holes because, again, we think that all black holes are rotating. Here's an example of the motion of objects. This is, sorry, let me explain. This collection of stars is a copy from measured astronomical data for the Milky Way. This over here is a black hole in a computer simulation showing you how the gravity of this black hole would distort the positions and velocities of a distant collection of stars that are behind this event horizon. And you can see in some cases the motion is reversed. That is, some objects are going upward in this computer simulation, and some are going down. Videos of this type were prominent in the movie Interstellar and were accurately depicted for the astronomical objects they used in that science fiction film. And what's happening there is, if you have your camera here, and here's the black hole with its accretion disk, light from here on this side, or light from objects more distant, for example, a background of the Milky Way stars, that light that comes near the event horizon has to travel on a curved path. The gravitational influence of the black hole is so profound that light, even from this spot on the other side of the accretion disk, will loop around and come to your camera like that. Suppose you have two black holes together. What does that look like? I'm just going to show a part of this. It's a 3-minute video. You can see two black holes orbiting around one another, and we know this happens because we have gravitational wave sensors that show the merger of black holes. And that's not included in this presentation, but these two objects start distorting each other's space-time. And stop it here for a second. This light that comes to your camera from this black hole, the center of which is right there, this is how you would how the distant part of the accretion disk would appear to you, because this light is coming up and over the event horizon. This part is the part of the accretion disk closest to you, and then part of the accretion disk comes under. So you see this sort of shape. And same for this other object. Let's jump ahead. I want you to see. Sorry about the sound, but these two are going to merge, and we would detect this with the gravitational wave sensors we have here in the United States, in Italy, and Japan. Stop that. So yet again, here's what I was trying to describe. Here's the accretion disk without the influence of the black hole, which is, we're going to put it right there in the center. And then we see this part of the accretion disk coming over the top to our camera. And we see, similarly, some of that coming underneath. That's what this line depicts, to our camera. So this is typically how you would see the distant, you would see the accretion disk and the distant stars of this black hole. If you're interested in this and the history or the development of the movie Interstellar, here's reference to the book that the producer of the film, Kip Thorne, who was a Nobel Prize winner in gravitational physics, he wrote a book about the movie and explained how the animations were done. They're science-based animations. And the imaging that was done was expanded or improved when we invented something called the Event Horizon Telescope, which uses radio telescopes to view black holes. Here's an X-ray telescope picture of that jet that I talked about. This is from a space-based X-ray telescope. Here's what happens when we look at a black hole, and this is an actual image of a black hole using the Event Horizon Telescope, which brought together data created by about a dozen radio telescopes distributed around Earth, all looking at a black hole in a nearby galaxy. And this is what we see. It's pretty much like what I just showed you in the animations. The interesting thing is, over time, they've taken additional pictures, and you can see these bright areas changing shape and moving around as the black hole digests whatever is in its neighborhood. So here's a link. You can click on that and probably get more recent images of this black hole that was first. The image at first was introduced in 2019, 6.5 billion solar mass black hole. Andrew Hamilton, who's a professor at the University of Colorado, is world famous for his work in animations of Einstein's equations. And here's Kip Thorne, the cover of Kip Thorne's book. If you click on these, you can see all sorts of images and animations that Andrew Hamilton has created with his students. These are not science fiction. These are the actual equations, and they're very entertaining to watch, but they contain science. His students are constantly finding out new things about rotating and non-rotating black holes by making animations and studying what they see. No, we're not going to do that. We're going to skip this because I want you to see something else. And there's information about a pending merger of black holes. You can read about this. How are we doing in terms of questions? Let's see. We have more in the chat box. So speak up if you have a question. Okay, no questions, and that's good because I have about 10 minutes to tell you the story of neutrinos. I mentioned that neutrinos, for my purposes in this lecture, I treat as part of the dark universe because we cannot see them with our eyes or telescopes. We need special instrumentation, and even then, it's really difficult. And the knowledge we have about solar neutrinos, or about neutrinos, comes from what we know about the dynamics of the center of the sun. And the sun produces, of course, energy we exploit and creates heavy atoms, but it produces astonishing numbers of neutrinos during that process. This is not until, say, the late 1950s has this process been fully understood. And you should also know that neutrinos were predicted in 1930 to overcome a problem in quantum mechanics that was baffling people. And somebody said, Enrico Fermi, in fact, said, we need a new particle that we've never seen before. And if that exists, it solves all these confusion that we have. And it took years and years to actually find neutrinos. They're very hard to find. I'll give you a kind of a rule of thumb. The typical neutrino can go through 100 light years of lead, not miles, not light years, 100 light years of lead before it interacts with the atomic matter in lead. And only because we have so many neutrinos to work with, are we able to find them. So Hans Bethe in the 1930s explained energy production in the sun, and in the process, this process produces all these, the hydrogen produces neutrinos here and here, and you need pairs of these to produce isotopes of helium, and eventually you produce helium, but you have produced also photons or particles of, well, in this case, gamma rays that eventually find their way out of the sun and become the light that we use for heat and so forth. When you build a detector for neutrinos, which was done in the 60s in a mine way below ground in South Dakota, you make measurements and compare the measurements with the theory, you do not get what you should. The theory predicts 3 times as much as you actually detect. Let me show you. So that caused a lot of tears. But that was exciting and energizing to discover that the theory for how the sun functions appears to work properly, except it doesn't predict the right amount of neutrinos. And it took years to realize that the Homestake experiment in South Dakota used carbon tetrachloride, used to be used in cleaning clothes, a huge container of carbon tetrachloride. And this carbon tetrachloride is able to detect one of the 3 types of neutrinos, 2 of which had not been imagined when this experiment was built. It was known that electrons in their various interactions have associated with them an electron neutrino. What was not known was that this detection scheme could not find the other 2 types of neutrinos. So the chronology here is the prediction of the neutrino in 1930. Then came the discovery in the 1940s that the electron has a heavier partner, a cousin. It's a charged particle that behaves like an electron in many ways, and it's part of the 3-part electron family. The muon is heavier than the electron, and the tau, which was predicted in 1974 and found in 1977, those 3 each have an associated neutrino, and the detections, you can see the dates here, it took a long time to figure this out and build experiments to detect these various kinds of neutrinos. By the way, 65 billion neutrinos go through every square centimeter of your body every second. And gradually, there was understanding that there are 3 types of electrons, each with its own neutrino, and those neutrinos have antiparticles, antineutrinos. So the theory of how the sun produces energy was refined, but there were still questions because the model we have for how the sun produces energy depends on the temperature deep in the sun. And we have no mechanism for actually going there and making that measurement. However, there's a field called helioseismology. You all know what seismology is here on Earth. Helioseismology studies the behavior of the surface of the sun, the dynamics of the shape of the sun, and from that, they can predict the temperature deep inside the sun. And it took advances in this kind of science to improve our understanding of how the sun produces energy. It confirmed Hans Bethe's theory, except there weren't enough neutrinos being detected. So a new source of neutrinos was explored, and that is cosmic rays, which strike the upper atmosphere constantly and produce a shower of subatomic particles, many of which are neutrinos. And it became obvious that if you could study neutrinos coming from above the atmosphere, on two different sides of Earth, you would be able to characterize the lifetime of neutrinos. In this case, the neutrino is created above the ground, say maybe 15 miles above the ground. But if you could detect neutrinos coming from the other direction, those neutrinos would have to go through planet Earth. They never noticed planet Earth, but we could determine something about their behavior. And so the experiment was done this way, that we have a detector, not only can detect neutrinos, it can detect where they're coming from. Some of them are coming from the upper atmosphere. The others are produced in the upper atmosphere, but have to propagate through Earth to get to the detector, in this case, a detector called Super K in Japan. With that data, we discovered that neutrinos change their behavior and morph from one to another to yet another. 3 different kinds of neutrinos appear and disappear as neutrinos travel. And the most prolific source we have is from the sun. So it turns out that this experiment in Sudbury, Canada, produced results that explained the dilemma that people had struggled with, because it found that here's the sun and neutrinos propagating towards Earth, that along the way, the neutrinos indicated here by blue, green, and red change from one state to another all the way along that trip. They keep changing what is called flavor. And with that discovery, we suddenly got results. I showed them on the previous page, an indicator of what we should have gotten. These numbers should have matched. Theory says we should have seen this number, and measurements now show this number. So there's sort of more work to do, but finally, the mystery of neutrinos have been resolved, and we understand that there's 3 types, each one associated with a member of the electron family, the electron, the muon, or the tau, and that these neutrinos keep changing from one configuration to another as they travel. So here are the Nobel Prizes awarded for neutrino research, for discovery of neutrinos, detection of them, creation of them, and eventually for a complete understanding of this element of the dark cosmos. And here's any of these that have a green circle around them are Nobel Prize winners I've met. So we're done for today. And thank you for your attention. And I'll see you next week when we're going to talk about the instrumentation technology that is used to do astrophysics and cosmology. Okay? Thank
Can
you
you
so much.
answer the chat, Ed?
Oh, yes. I got to make sure I have the chat recorded. Okay, I think we're good. Thank you, everybody. I'll see you next time.
Thanks,
Okay,
Ed.
thank you.
Thanks,
Okay.
Ed.
Bye.
You've got everything, Ed? You got all the questions and stuff?
Yeah, now I'm eager to see what happens when you end the session. Am I actually going to get my video? But
I
go
hope
ahead.
so. It's been recording the entire time. I promise I've been watching.
Okay, very good. Thank you so much.
All right, I will see you next week.
Yep. Good day.